Hello, we are Team 12 and we are presenting an analysis and redesign of an air fryer. As a product, air fryers crisp food by adding and circulating hot air as an alternative to frying with oil. The primary customer group are single-family households adopting a healthier lifestyle, whereas a secondary customer group are small business coffee shops and hotel self-serve breakfasts. We looked at a few models of air fryers, particularly the Ninja. We wanted to take a few features from each of the models and make a representative CAD model. Shown below is the exploded view of our representation.
The primary function of an air fryer is to crisp food. In order to do that, it needs to hold food, warm food by adding air and adding heat, control airflow by circulating air and removing air, assure convenience, enhance product, please senses, and assure dependability by preventing burns through sealing the environment and dissipating heat, as well as avoiding electrocution to the user.
For our air fryer, we have two different assembly sequences. Both begin with the bottom shell, followed by the cooking chamber, bracket, heating element, and grate. Assembly A adds the top shell subassembly, then the door subassembly, whereas Assembly B adds the door subassembly, followed by the top shell subassembly, and both end with the rubber feet. When comparing the two assembly sequences, Sequence B proves to be the more desirable sequence because when adding the door subassembly first, it's easier to locate and join parts.
This is our finalized bill of materials showing a breakdown of the manufacturing and assembly costs for the air fryer. Injection molded parts will be made using ABS plastic, while parts requiring a higher operating temperature will be fabricated using stainless steel sheet metal. For cost calculations, we assumed a production volume of 1 million units and a labor rate of $15 per hour. Our redesigned air fryer has an estimated production cost of $85.97, which is 32% lower than the cost of our original design.
Seen here is the function component mapping matrix. Half of the 14 parts outlined serve more than one function, with majority of them contributing to either or both holding the food and sealing the environment. This indicates that there's plenty of room for a potential redesign in how an air fryer holds food or seals its environment, but less flexibility in redesigning how it adds heat, for example, since only one component serves that function.
The air fryer will offer the same basic functionality regardless of whether it's designed with a consumer or commercial use case in mind. Both products will need to add, remove, and circulate air, which is basic platform functionality, as well as be safe for the user. However, differences in desired functionality become apparent when we further investigate the needs of the two different groups. Consumers might be using it to make a dish for a meal once or twice a day, whereas the commercial environment may be using it many times a day to warm up food for customers and potentially want to do different foods at the same time. As a result, the commercial application would need to be differentiated from the consumer application with increased durability, functionality, speed, and ease of use. As a result of these identified differences, we explored several different opportunities to redesign the air fryer to improve manufacturing efficiency, reduce part count and cost, all while increasing durability and ease of use for consumers.
Differentiation between our two product variants occurs with the top shell subassembly, and in our new sequence, this is the very last step. Now that we focus on the primary product variant, being the air fryer for single-family use, we begin with design for manual assembly. From the chart, we could see that the assembly time is quite high at 282 seconds, and the assembly efficiency is quite low at 19%, which can be attributed to the amount of fasteners that we need within the cooking chamber. After making 3 redesigns, we can see that we save 131 seconds of assembly time and improve the efficiency by 8.74%. Our first redesign was of the hinge that connects the door to the bottom shell. We increased symmetry, decreased fasteners, and added depressions to facilitate part orientation, thereby incorporating DFAS1, DFJ1, DFJ4, DFPH1, and DFPH2. Our second redesign eliminated the fasteners that connect the top shell to the bottom shell and replaced them with snap fits, thereby incorporating DFJ1, DFJ3, and DFAS1. Our third redesign eliminated the 4 rubber feet and consolidated them into the bottom shell, thereby incorporating DFAS1 and DFPI3.
We redesigned the door subassembly to allow for automated assembly. Initially, it was difficult to align the holes for fastening the hinge in the door, and so we changed it to studs on the hinge to act as locating features and allow for Z-assembly. In addition, we used the handle to hold the door in the assembly fixture, as well as exaggerated features on the seal groove and gasket to facilitate orientation and secure the seal in place. This resulted in a total savings of $2.44.
Both the upper and lower housings were analyzed for process selection. Based on market size estimations, we anticipate a combined production run of approximately 1 million units. ABS was chosen for its high strength-to-weight ratio, aesthetics, and impact strength. Using snap fits and redesign dictates use of a non-metal, and based on this, candidate processes are shown below. For both components, part shape, 3D and hollow, as well as mass, makes compression molding, thermoforming, and blow molding unsuitable. For the upper housing, snap fits on the redesign dictates a 0.3 mm tolerance, which is comfortably in the middle of the capabilities for injection molding and machining, but right on the edge of the capabilities of rotational molding. For the lower shell, the feet are redesigned to be integrated into the shell, which have a 0.1 mm parallelism tolerance to prevent wobbling. This is outside the tolerance range of rotational molding, and so machining and injection molding are the only suitable processes. The large batch size is on the edge of machining's capability, and as a result, injection molding was chosen for both components, as all criteria sit comfortably in the middle of process capabilities.
Now that a manufacturing process has been chosen, we must analyze the cost of injection molding the top and bottom outer shell of our air fryer and consider redesigns that would decrease this cost. The manufacturing cost estimation was done with the assumption that both pieces would be made out of ABS, have a tolerance level of 2, with several tolerances, approximately 25 millimeters, be injection molded into a single cavity mold with a flat parting plate, and have a desired opaque standard surface finish. With these assumptions, the top shell before redesign had a total injection molding cost of $4.37 per part. To decrease this cost, and to aid in the ease of manual assembly, the screw tabs were integrated into the top shell as snap fasteners, allowing for a reduction in the number of side pulls. Additionally, the thickness of the topmost surface was halved, and a fillet was added to replace a hard edge. These changes decreased the amount of material required overall and severely decreased the cycle time, allowing for a 31% decrease in the manufacturing cost to only $3.02 per part.
The injection molding cost of the bottom shell before redesign was $17.59. The original design had a high maximum wall thickness due to the integrated feet on the base of the part. We minimized the cross-sectional thickness by eliminating material, leaving 1/8-inch thick cylindrical feet to raise the base of the air fryer. Additionally, the alignment slots and screw holes were replaced with snap fit joints, improving manufacturability by reducing the number of side pulls required. We also eliminated sharp corners by adding 1/4-inch fillets to the interior of the part. These changes decreased the injection molding cost by 42%, bringing the cost down to $10.28 per part.
With growing competition, companies have been starting to introduce added products and services that complement their existing product line. These are known as product service systems. For the case of culinary products, adding a service such as an included recipe book or a specialized tutorial blog could help customers to learn how to better use their product and also increase awareness of the product. There has also been a growing concern to reduce environmental impact. For example, we could introduce a special warranty service repair that could be provided at the time of purchase. In the event of a repair being needed, the customer could send that defective product back to the manufacturer for servicing. Instead of just sending a brand new product, having it repaired would cut down on wasted material. The guarantee of an unlimited warranty could also build trust between the customer and the company. Thank you for listening.